this is your first day? Yeah. First day, okay. This is the course outline. I handed this out to first day class on Friday. It's got answers to it. I handed this out yesterday. We started working on a package. I handed out some paragraphs too. Okay, can I just get this story name? J? Yeah, J-U. J-U, and your first name? Is this your first time out of school? Did you just come to look at it, or did you been here for a while? In your home country? Yeah. Okay. South Korea, okay. Interesting. How did you find us? How did you find our school? What do you want to study in our school? Psychology? Did some of your friends graduate from this school? No. What's her name, by the way? Because I had a student from South Korea last year, and it was her. Alright, so welcome everyone. As I said, the first thing we're going to do is, sorry. Yeah, you've got to pop up those. Yeah, pop them up. Are they going up? Unlock them? Yeah. Now. Yeah. You can do that, right? We started our transformations. I'll give you this too. I know it's a little confusing at the beginning, all these booklets and papers. I try to minimize the use papers, but this is basically our go-to booklet. This is how we run most of our math courses. This is your go-to examples booklet. This is where all your work and your notes will be, right? And then your actual homework is in your textbook, which has not arrived yet. I had the court contact the publisher again yesterday. But your textbook will be a big published textbook that looks like a so it'll be a little less confusing when the textbooks arrive, right? But this is our day-to-day examples book where I do the examples, I'll show you how the work is done, and you take your notes in here. Okay? So yesterday we started transformations, and we learned a little bit about, you're going to need all the paperwork that you missed, Aminette? Oh, you're going to need all this? So I did answer a few questions from the homework assignment, but were there any last questions on this homework assignment that you wanted to talk about on page, I don't even know what page 9, page 9. Any last questions here? No? Okay. Number 5. Which one, Abdullahi? D? The very last one? So this is in that function notation. It says find, it's basically find f at the value 2. So it's saying find f, find the function value, find y when x is a half. That's what this means, right? This means find y when x equals a half. Okay, well here's your set of instructions right here, right? So f at a half equals 2, I'm just following my sets of instructions, a half squared minus a half. What's a half squared? Quarter? You have to be good at fractions, by the way, in pre-cal. There's going to be lots of fractions, especially in the trigonometry unit. And remember, you don't have access to your calculator the whole time. So 2/4, I get 2/4 minus a half. Well, 2/4 is a half, right? So a half minus a half, after all that work, I end up with a value of 0. Okay? All right, we will be moving on with this booklet. As I said, I'm not going to be doing the conceptual approach because that's not part of this course. So I'm not going to go over these notes, but by all means, if you want to look at it, you can learn a bit of vocabulary, I suppose, but we're not doing those skills in this class. So I'm just going to leave this book aside for a moment, and we're going to return to our examples that were where we left off yesterday. I'll take attendance a little later in the class when I'm sure that everyone has arrived, because there's some movement back and forth. All right, so I think we left off. So what I'm going to do is I'm going to finish up these examples, and then I'm going to give you some work time in class again, and I might do a little bit of a break and get you to do some work in the interim. So we were on page 6, and we had just finished transforming a graph, and what we were doing yesterday, there are, I guess depending on how you classify them, there are 4 different transformations. So the family of transformations of functions, just to recap. Okay. So remember, a function is just a relationship that we can graph on the xy axis. Not all things that we graph on that xy grid are functions, right? It has to pass the vertical line test. And the functions are what's important to us as math and science people. Okay.
So we're not doing 1.2?
Yeah, no, we're not doing 1.2. We're going to skip to 1.3. So transformations of functions. The first type of transformation we're doing, the word's it's a little funny because translation kind of starts out like transformations. But we talked about translations yesterday. And you're going to get a little time to do some, we're going to finish up translations today, and we might start with impressions. What's I guess, an everyday word for translation? What would you use, or what have I used in class for translation? I never said translated right, translated left. What did I say? Shifting, right? These are the shifts. So I'll usually use that in class, but it's just a shift left or right, up or down, right? So it shifts left, right, and or up, down. The reason I'm saying this, and this is all review, right? The reason I'm saying and or is because sometimes you might get a horizontal translation, sometimes you might get a vertical translation, sometimes you might get both, right? The next type of translation we'll do, they're called stretches and compressions. And that's basically, they narrow and widen the graph. Narrow or widen the graph. I briefly introduced you to another type of transformation. Reflection, right? The graph. Okay, I'm going to use another layman's term, or like an everyday term. I could say reflected, but that kind of doesn't give you any more insight, right? Reflected, I like to say, sometimes I'll say flipped. Right? So when I say flipped, it's just flipped over, right? Flipped over the y-axis, x-axis, or the line y equals x, right? basically what these do. They change a given graph. So the only thing, I think this is pretty well, not self-explanatory, it's pretty easy to comprehend. It gets tricky when you have a graph that has been transformed with all of these, right? With a translation and a stretch and a reflection. Those are the tricky ones. And at the very end of our workbook unit and the end of your chapter, that's when we do those graphs that have all the transformations on them. Right now we're just studying them one by one. So we're kind of just doing 1 or 2 translations, 1 or 2 stretches, 1 or 2 reflections. We're not doing them all together, but we will very shortly. The tricky part is you can be given just a generic f of x graph where you don't know the equation, or you can be given the actual equation. And we're going to get a little deeper into that today. That's about the only confusion I can see that would come up. So yesterday we just made it through half of the examples on the shifts, right? The translations. And you can see I did this one, this graph. It was easy enough. It just said translate 4 up, 4 left, translate 1 up. So we did that. I just took my original graph, which was in black, and we physically just moved the points, right? It's very easy to do that. If you're just doing a translation, that's probably the easiest way to do it, right? On my second one, though, I actually created, it looks like a table of values, but this is called mapping. And why I did it that way is just to introduce you to what mapping is. Now, was it necessary to do mapping for this question? Probably not, because I think it would still have been easy to identify. We did have to identify some points, to identify the points and shift 4 to the right, 5 down. I could have done this. 1, 2, 3, 4. Is that what it was? 4 to the right and 5 down. What happened here? Sorry, I know why. Because the scale is off, sorry. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, I could have done that too, but the scale threw me off a bit too there. I could have physically just transformed the points because shifting is easy, but I wanted to introduce you to mapping. So I'm just going to say this technique, this method is called mapping. And I'll be using this a lot. You can see why this might be useful when we have a function transformation involving 5 different transformations, right? 5 different math steps. Then a really organized, clear system is easy. You just pick your critical points, perform the math, and it's much easier to handle with that. Hang on, let me grab all this stuff. We're in the purple booklet right now. Okay, the only thing we didn't finish up yesterday is we didn't finish up the domain and range. So, who wants to give me the domain and the range of this, it says of each function. So I'm going to call, this one is j of x, right? This is, let's do the domain and range. Maybe I'll make a little chart. I'll say the original function, and I'll say the transformed function. Okay, the original function in black. What's the domain of this function? What are all the possible x values? Look side to side. How does the graph grow side to side? Yeah. So negative infinity to positive infinity. How about the transformed function? What's the domain? Same, right? What's the range of this function? 0 to infinity. And what's the range of this function? -5. Okay. Just as an aside, how many people prefer interval notation? How many people like set notation? Well, it looks like the intervals won't because, and the rest of you are undecided. So I'll try and flip back and forth between the two just to keep you exposed to both.
What's the difference between original and
Well, this is the original function. This is the transformed one. Okay, this one's been moved down and over. Okay. Okay, let's go. We're going to do a couple more examples, and then I might break and get you to do some homework questions, and then we'll finish up the examples. Example 3, here's the graph of g of x. On the same grid, sketch the graph of each function below, state the domain and range of each. Okay, is this easy enough to do just without doing a chart? Transformed graph, do you think? Could you just do it by hand? Yeah? No? What if I identify a couple points for you? What if I identify, I don't know if this one is going to work. We'll try it. We identify this one, this one, this one. You can't do it without identifying some points, right? You notice on our very first example, the points were clearly identified for you. But if they're not, you got to pick some points. Does it matter which points you pick? Not really. But you want to pick the important points, right? The corners, kind of the point of symmetry. If I identified those points for you, could you do these two? There's two transformations here, right? Okay, I'm going to introduce you to a word today. I'm going to say describe. When you see the word describe in math, if you haven't heard it in previous math courses, in pre-cal, the word describe or explain means you have to use words in your answers. So you're going to see a lot of describe too. So describe the transformations. Who could describe them for me? Just verbally. Could you describe them? Anyone? What are the transformations you see? Yeah. Shift. How many units? 3 units to the right. Yeah, and 2 up. That's all we want. You don't have to write any formal sentence. You can even just do it bullet form. Okay, so if I do that, 3 to the right, 2 up, I think I could do it without a chart. Do you think? Okay, 1, 2, 3, 1, 2. Again, it's really important you do this. It looks like the simplest thing in the world, and it is, but you'd be surprised how many people get lost in graphing if you don't have a system. Notice I said to you, go left to right. If you don't go left to right, do you know what's going to happen? You do this point and then you do this one and you can't remember the order, right? So move left to right. So 3 to the right and 2 up. 3 to the right and 2 up. I'm kind of off, so I'm guessing this one a bit. 1, 2, 3. I'm doing the best I can, right, with the grid. 1, 2, 3, 2 up. Okay. I recorded my points left to right, and so that's the order I'm going to draw them in. And pay attention to the shape. This is a sharp corner, right? You could even use a ruler. This has to be rounded. It's very important. The difference between a rounded join and a corner are the difference between full marks and half marks, right? Your graph, your picture should still look the same. The only thing is it's been shifted, right? If your graph has arrows, you have to include the arrowheads. If there's no arrowhead, for example, if this was just a point, then this one is just a point, right? Because points mean, an end point means the graph ends there. But the arrowheads mean it continues on to infinity, right? Okay, I have to label this one. So this is going to be my pencil graph is y equals f x minus 3 plus 2. This is that special function notation, right? If the f is in it, I don't know what the equation is. They're just telling me that the original function is f of x, and the transformations you see, I know because the 3 is inside of the x, it's a horizontal shift, and the 2 is out. Can you see the 2 is outside the function? So it's attached to the y, because f of x is like another name for the y. So any number outside the f is moving the y-axis, right? Or moving on the y-axis. So again, if you're just given the generic, actually this should have said an f too. Wait, there's typos here. This should have been an f. Just because they gave us f in the question, okay? So they didn't give us the equation, they just gave f of x, that's going to be important. Don't know what the equation is, it doesn't really matter. They just gave me the changes on f, I interpreted the changes, I graphed. Here, What are the changes you see here? Could you describe them for me? The same kind of way here.
Y equal
One down, two
left.
to the left. Yeah. So this one I'll do in red pen maybe, so it looks different. So this is shift 2 to the left and 1 down. Okay? Normally you're like, some textbooks would have written this as this, right? F of x plus 2. And in y equals form, because that was negative 1, you can see clearly that's a 1 down. So once again, I'm just going to pick my critical points of my original graph. 2 to the left and 1 down. 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 And finally, 2 left, 1 down. Connect the points, sharp corners, rounded middle, sharp corner, ending with arrowheads. And I guess just to complete everything, we'll do the domain and range. The domain and range of the transformed graph of the penciled graph. Domain, you can see if the arrowheads are on either end, domain is always going to be. Okay, this time I'll do it in set notation. And I will accept XER, and some people are doing a little more fancy. They're saying X such that, XER, and that's fine. You can get by with just XER if you want. And the range, what's the range? Let's see, anything greater than or equal to 2, right? Now, I will accept, again, you can just write this down, just so you guys know. They've relaxed a lot on the set notation. You can just write it like this, x greater than equal to 2, okay? Or, if you learned from a really strict teacher, which is great, you can say this, y greater than equal to 2. For my, is that what school were you at before again? St. Boniface. Is that what they did? Y such that, y? Yeah.
Yes.
So keep doing that if you're used to doing that. It's much more formal. It's nice. Okay. Now, let's do the red graph. Domain, of course, same. And like I say, I will accept this too, XER. And the range, what? Y greater than equal to negative 1? Agreed? Okay, so that's pretty straightforward. So hopefully you're comfortable with the first skill we were doing in these examples was just graphing a transformation given a graph. I think everyone here probably can handle that, right? The hardest thing is picking a couple of critical points, right? Picking points that will help you graph. So pick points on either end, pick one in the middle. If you can get by with just 3 critical points, transform them, great. But your original shape from a shift, your original shape should be the same size, right? It's just shifting around. Now let's get to a few different styles of questions. Okay, let's do some of these styles. When we flip the page over, no picture, so we have to interpret the given instructions. Determine the coordinates of image points after a translation. What an image point is, an image point, for example, I'll just flip over for a second, I'll show you what an image point is. On my original graph, here was my original graph, right? Let's say I call this A. Okay? This point, when I transformed it, my first transformation, A moved to here, right? I can't call this A again, because A's already been used. It's actually the image of A, so how we say that would be A primed, or A with a little mark. That means it's just the image point. It's the new A. Okay, that's what the image point means. This also could have been new A. I'll put it in red. This was the new A, right? The image point after it was shifted. That's all we mean by image points. They have their matching counterpoints in a new location. Okay, so they're saying The point A was 2, 5. It lies on just a generic f of x graph, so I don't know what that graph is. It could be a line, it could be a quadratic, who knows? What are the coordinates of its image point, and you've got this little a primed, on the graph of y minus 5 f of x plus 4? Okay, can you figure out what they're asking? So what do you have to know? You have to be able to know to interpret the language, right? And what is this telling you? Yeah, it's saying what? Shift? 4 left? Up 5. Okay, because really that 5, if we move it over, becomes positive. Okay, now I didn't have to write that down, but of course I'm writing that down for notes and for the video later. So if you can just think of this as a bubble in your head. Now, what is that mathematically? Mathematically, that 4, it's x minus 4, right? So I'm going to show you, like if I was shown using mapping, a mapping technique, the mapping shows the math involved, okay? The points, or the point becomes, and Johannes, you're right? What happens is I take whatever my x coordinate is, and if I'm moving to the left, it's a subtract 4, right? So I subtract 4 from my x coordinate, and then what happens with y? Y plus 5. Right? That's the math that gets involved, right? Okay, so what happens here? I had a 2, so this becomes 2 minus 4, and what? 5 plus 5. So my point originally becomes negative 2, 10. Okay, is the coordinates, or are the coordinates, right, of point A primed. Okay? Now, once again, to answer the question, you don't need to show me all that work. You could have just said in your head, okay, well that's going to be 2 minus 4 is negative 2, 5 plus 5 is 10. Give me the answer, that's fine. Let's try B. The point B lies on a generic graph f of x. What are the coordinates of its image point on the graph of f of x minus 2 minus 6? Okay, I'm going to get you to try that one on your own. Write the answer down before I do. We'll see if we agree. Okay, anyone want to be brave? Anyone? Eduardo got 1, 1. Anyone agree? I do. Okay, I got 1, 1 too. Because what do we have here, Eduardo? We have a shift to the right, 2, and down 6, right? So I would have done negative 1 minus 1. That's my x value, right? That would be, sorry, negative 1 plus 2 gives me 1. And my y coordinate, 7 minus 6, also gives me 1. So point B primed is 1, 1, right? All right. The same principle, example 5 is exactly like example 4. All right? Exactly. Determine new domains and ranges after translation. So I don't just want an image point. I don't want just one point. I want the whole new domain and range. See if you can figure out what to do here. The function f of x is just a generic function, has a domain from -3 to +5 and a range from +4 to +10. What are the new domain and range after these changes? Let's identify the changes. What do we have here? What are these? What's the x plus 8? What happens there? Shift 8 left and 2 down. Okay, with that information, could we come up with a new domain? If I told you it's the same thing you were doing in example 4. What did you do in example 4? You took the x coordinate and you just either added or subtracted. So if I shift 8 left, what am I doing to my x values? Subtracting 8, right? For my new domain, subtract 8 from each x value. Now instead of just 1, there's 2 of them, right? If you think about it, all you're doing is, think about it logically. I don't know what, it's kind of hard, right? Because you don't know what graph we're talking about. All you know is my original graph, my y plus f of x graph, took place between 3 and 5, right? Maybe it was one of those weird ones that we saw on that one, right? Maybe it was one of these. Let's just pretend it was one of those. Well, what would happen if I told you this was shifted 8 units to the left and, what was it, 2 down? Okay. Let's just do the 8 units to the left. What would happen if I just shifted this 8 units to the left? Where would it arrive? 8 units to the left, -11, 8 to the left, -3. That's it, right? You're just taking 8 away. Like, it doesn't really matter what the graph looks like. So my new domain is from -11 to -3, correct? Okay, so that's it. That's my new domain. So we would say -11 less than equal to x less than equal to -3. And my new range, what do I have to do? Subtract 2 from each y value. And that becomes 2 less than equal y less than equal 8. That's it. You're kind of just doing that technique you did up here twice, right, for each endpoint. Okay, let's try a couple of equations and then we'll see. I'll finish 6 and 7 maybe, and then we'll talk about your homework in the book for the first part of the class. Okay. Determining a new equation. You can see when we were, like, you know how I said equations and graphs go together all the time? Here, you were given, in this example, remember example 3, we were given the new equation. We had to sketch the new graph. Here, they're kind of just giving you instructions, and they want you to come up with a new equation, right? To alter the equation. Now, it says the graph of y equals 1 over x is translated 3 units to the left and 2 up. What's the equation of the image graph? Okay, so this time you can see I'm actually given a real function. It's not just a generic f of x function. I know what this guy looks like. This is my reciprocal function, right? So I don't have any f's in here, so I'm not going to respond in that using f notation. If I'm given the f, I have to respond with the f in the notation. But here, this is just a reciprocal graph. So translated 3 left and 2 units up. So this is my starting graph. Y equals 1 over x. The 3 is a horizontal translation, right? This is a horizontal translation. Horizontal shift. Which variable does a horizontal affect? X or Y? X, right? So this change is operating on the X coordinate. So 3 to the left means the X is shifted, correct? Now, 2 up, this is a vertical shift, right? So the Y is affected, the whole function value is affected. When the whole function value is affected, whatever you had here, yeah, the +2 just goes on the end like that. Okay? We haven't done that yet. No, that half wouldn't be there. No, don't put the F. If the F's not given, don't put it. Okay, what about this one? The graph of y equals 1 over x squared is translated 4 units to the right and 1 unit down. Okay, we have to be careful about this one. 4 units to the right and 1 unit down. So 4 to the right again is horizontal, right? And this is vertical. The vertical is easy, right? Because it's just attached to the end. But y equals, remember it's x, the x value that's affected, right? Remember what happened when you had a quadratic function in grade 11 with that vertex? It's exactly the same thing. When you had quadratics, right? If I had my classic quadratic, right, and y equals x squared, what happened when this shape, no other changes, I just shifted to the right by 4, this is 0, and it got shifted to 4. What did the new equation become? X minus 4 all squared, right? It's the same thing. When it shifted up to 4, it was a vertical shift, right? Nothing happened to x, he stayed x squared. But the vertical shift, the +4 just gets out to the end, right? Same thing, nothing, no contradictions in math. We don't contradict from grade to grade, right? We just keep building. So anything affecting the x gets attached with the x within inside the brackets or underneath the radical sign, within absolute value bars. It's always nestled with the x. Okay, what about this one? The graph of y equals root of x is translated 7 units right, 3 units up. What's the equation of the image graph? I'm going to give you a sec to try that one. Okay, anyone want to be brave for me?
Y root x.
Root x.
-7.
Does the -7 go here or here?
No.
Here?
Yes. And
+3, right? And the 3's outside? Agreed? Okay, that's it. Okay, let's try that. Let's try one more example, and then I'm going to give you some time to work on the assignment in class, the next assignment, and then we'll start stretches and compressions probably in the second part of the class. So example 7, the graph of g of x is the image of f of x. Okay, so g, and you can see all the points on g are marked with a primed, b primed, or a and b primed. So this is my original graph f of x. It's got the regular a, the regular b. This a has transformed to this a, this b to this b. Write an equation of the image graph in terms of the function f, okay? So this is f of x. Can you determine what changes have been made that shifted f, the solid graph, to the dotted graph? Okay, what were the changes made? Can we describe the changes first? 1, 2, 3. 1, 2, 3, 4. Okay, so shift to the right 3 and shift 4 up, right? Now it says, the only tricky thing is, so that's easy enough, right? We can describe the changes, but to answer in the proper math language, write an equation of the image graph in terms of f. So this is what they want. So g of x equaled, okay, so what happened was, in terms of f, that means they want f of x, I'm doing this very lightly, they want f of x in the answer. That's what in terms of means. So if I leave f of x in the answer, because I kind of have to in this case, because I don't know what these functions are, so how do I demonstrate that how do I incorporate this shift right 3 and 4 up into this f of x statement? I have to make changes on f of x to show that it was a shift right 3 and 4 up. Do I have to put anything inside brackets? Okay.
Minus 3.
So I show minus 3 here, right? Plus 4. Exactly. Because they said the only thing they have for me is the function in f of x form, if they give it to me in f of x form, I have to use that f of x in my answer. Okay?
Why is it
It could be, I guess I just said write an equation of the image graph and they told me y equals g of x, or it could be because they're both the same. They just said the image graph, they called the image graph g of x, so I just kept it as g of x. That's why.
But what if it minus 3 is just right and it's not like a quadratic, right? Should it be plus 3 or minus?
Well, it was a shift to the right, correct? So any shift to the right is a minus 3. If it's a shift left, because it's shifting 3, because your actual, okay, so this is the standard, let me show you standard form for an f of x, let's see, for f of x translations. Okay, so this is what happens. Okay, it would be y equals f x minus h plus k. If k is positive, I move my graph up. If k is negative, I move my graph down. If h is positive, I move my graph to the right. But if it's negative, what happens? See, if h is negative, that becomes a plus sign. Right? That's why plus is negative. If h is negative, it moves left. The negative is part of the equation. I guess, okay. You know how you said to me, this is a shift, right? Agreed? So if it's an x minus h your, oops, I need to work on that. This is your quadratic, right? X minus h squared plus k. H comma k are your vertex, right?
Yeah, so we're not getting lost in the actual quadratic, right? There's no square.
Yeah, but this isn't a quadratic graph, right? This isn't a quadratic. It's a cubic graph, yeah. Like the only way you'd see y equals x squared is if I gave you, if your original graph I gave you like that, right? But this isn't. This is cubic. Look.
Yeah.
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 So I'm still not clicking away.
I don't know, I'll see you at the next one.
Okay. This was just given to you as f of x, because we haven't actually learned cubics yet in this course. But actually, the real equation of this graph looks like, I kind of screwed it up, didn't I? I think that this is a pure cubic. I think this, if I really wanted to give you the actual, this would be y equals x cubed. Okay? That's the y, if I didn't put it in f of x form, right? It'd be y equals x cubed. So this is actually a good teachable moment. So let's do that. Let's do this. So that's a really good question. So let's say I said here, I'm going to scratch this out because I actually know the equation. I know the actual equation. I figured it out. It's y equals x cubed. Okay? If I wanted to do it proper, then the transformed graph would be, I wouldn't need any f's in it because it's not unknown to me anymore. It's still a shift 3 to the right, 4 up. So I would write it like this. Y equals x minus 3 cubed plus 4. That's what you mean, right? Is that what you meant?
Yeah.
Yeah. That's a really good question because your assignment kind of goes back and forth. Sometimes you're actually given the actual equation of the graph. Sometimes you're just given generic f of x. You have to learn to work with both. Does that make sense to everyone? If you're not given any x, then you just use the real equation. Yeah? What's another graph I could give you? Let's do this one. Let's do another one just really quickly. I'm going to stick to those ones that you kind of already know. What if I gave you one of those parent graphs I gave you? And I'll just, for interest's sake, this is 1 and 1, negative 1. So this is, does anyone recognize that graph? Yeah, absolute value graph, right? And this is 2, 2, 2, negative 2. What's the equation of the absolute value graph? Y equals x, absolute value, right? What if I told you, okay, I want you to draw the transformed graph. I want you to shift it, I don't know, someone do 2 shifts. 3, which way? Let's do 3 up and 2
Down.
no. Let's not complicate things anymore than we have to. Let's do 3 up, 2 to the left, okay? So if I did 3 up, 2 to the left, if I kind of just did this real quick, 3 up, 2 to the left, so I have to go, okay. So I'll do it in red. So 3 up, 2 to the left, okay. Pardon my, skills, but let's just do this quick. So that would be the new picture, right? Every picture has an equation. What would the new equation be attached to this picture then? I need the bars, right? I know my x is going to be in the bars. Should I make my bars a little wider? Okay. Because I might have to fit something else in there. Okay, what's inside the bars with x?
+2.
+2 and +3. Okay, that would be the new equation, right? Now, what if I didn't really, what if I'm just kind of trying to teach transformations to a grade 10 student? They haven't done anything with absolute value. They don't know any equations at all, but I just kind of want to teach in terms of F. Because you don't know anything about absolute value. You didn't learn any of that in grade 10 or 11. Your teacher forgot, okay? So what would you do? Okay, the best you could do for me is say, okay, well, I know there was a change on X, so I know that that's a 2 and that's a 3. Okay? So it's really the same skill. When you know the equation, you work with the equation. When you don't know the equation or you were given it, you just write it in terms of F. That's what we say. This approach allows us to throw at you a whole bunch of weird graphs that don't even have equations, right? Like those weird ones that we were, you know, like this allows us to do some weird ones like that. You know, that we don't even have to come up with the equation. We just say, okay, this is f of x. So you're going to have both styles of those. And I'm glad you asked that question because I was going to have to teach this a little later on in the second half. And now I don't have to as much. Because that's always the problem, right? Your exercises consist of some of these, just f of x, and then some of these, and you have to work between them, and your eyes have to recognize, oh yeah, she gave me the f of x, I'm just dealing with f of x now. Okay? Yeah? Okay. So that's a good question. I'm glad we got that sort of out of the way so I can... Okay, so that's why here, Eduardo, we're just sticking with f of x's. Okay, this one, now actually we're in the same situation, right? Because this is actually a radical, and you probably do have the skill to actually come up with the exact equation, but we're not going to spend time on that. We're just actually trying to just talk about transformations. So I'm not going to, can everyone recognize that this is actually a radical function? Okay, but I'm not worried about that. Let's just talk about transformations. So the graph of g of x is transformed from f of x. So it started as f, and then it got transformed to g. Write the equation of the image graph in terms of f. Okay, so I'm going to give you a sec. And let's just call this, I would call this one g of x again. I would just say g of x equals, okay? Because my new graph was my old graph, like f of x with some changes. So I'll give you a minute to do those. Did everyone else agree that it was 2 left, 5 down? Yeah? No? Let's see. 2 to the left. I moved from A to A primed, right? So 2 to the left. 1, 2, 3, 4, 5 down I got. Let's try B. 2 to the left. 1, 2, 3, 4, 5 down. Anyone else say 2 left, 5 down? Yeah? Okay, so in terms of F, I'd have to include my F this time. It'd be x plus 2 minus 5. Yeah? No, yeah, I said it's actually radical. It's a radical, but I just said write it in terms of f, right? It said in terms of f. Okay, so it says assignment time. So there's an assignment in the book. Because we're sort of new to this book, and I'm new to the book too. I've just been looking at it over the summer. It's new for me for teaching from this book. But one of the reasons I kind of chose this book. It gives us a little more info. So again, I'm going to just give you some time to do a short little assignment here. If you flip to page 19, because I flipped over the transformational approach. We don't do rotations in this class, and we don't do things like with rotating angles, so that's why I just flipped it. But by all means, if you want to take a look on your own time, go ahead. And then I'm on page 19, and it says, a more formal approach to transformations. Okay? And then what it does is I'm going to leave this with you. You can read this on your own time. It talks about graphing linear functions, a review, because this is old stuff, right? This is like grade 10 stuff, I think. But some people need that review, right? It's been a while. So it talks about graphing a linear function. We talked a little bit about this last Friday, I think, on our first day together. It says there's a couple of ways you can graph a linear. This is all stuff that you're expected to know. You can make a table of values, or you can do the quick way, right? The slope-intercept approach, which is probably the way I would prefer because it's quicker. You can do slope-intercept. So again, a little bit of review for you. And they talk about the parts, like the 2 is the y-intercept. The m value is the slope. Then it does a little review about graphing quadratics, which might appeal to people. Remember that little review, course review I gave day 1? We had a little bit of review with quadratics. It defines what a quadratic is, the ax squared plus bx plus c. So those are the 2 functions you're supposed to know quite well now, like the linear and then the quadratic, and we'll be building on those. Again, sketching quadratics, you can do your table of values, which is kind of time consuming, but it works. Meaning you just pick a bunch of values for x, substitute it into the equation you're given, and then you find your y, and then you have to plot them. There are better ways to graph though, just like linear, slope-intercept is quicker. You can learn how to put it in vertex form, right? And then it talks about the parts. So again, that's all review. If you need it, please review it. And then we get to horizontal and vertical translations, which we've just spent the last 2 days discussing. So this, again, you can review at your own pace and your own leisure because it kind of goes through what I've been talking to you about, but it formalizes things a bit more for you too, which I hope the notes pages do that for you. But basically this is a nice summary. In general, in an equation which describes any function, it's just saying if k is, what does that mean? K and that symbol 0. What does that mean? If k is greater than 0, right? So this means if k is greater than 0, which means if k is positive, just a fancy way. If k is positive, it moves up, right? If k down, negative, right? Moves or shifts down if k is negative. And then we move to the horizontal. X minus h will slide the graph h units horizontally right if h is positive, left if h is negative. Because if h is negative, a negative, negative, that's why you end up with a plus sign, okay? And then they reiterate it. If you have a plus k, we move up. Minus k, we move down. So they're just kind of telling you the same thing over and over, but repetition sticks a bit, right? And then they have some pictures for you. I'm kind of going over these notes with you to show you everything. So here they're actually giving me the graph, the y equals x squared graph, right? Then they're showing you, the only thing about this book, please get used to the fact, whatever graphing program they used, it doesn't include arrowheads, but it's supposed to, right? So when you see these graphs, they're supposed to be arrowheads. But the Pearson textbook that I used to use did the same thing, so it's nothing new. So there should be arrowheads, right? Okay, so you can see 2 units up, they give you the picture, they give you the equation, x squared plus 2. So you can use these 2 for notes too, right? 2 units down, x squared minus 2. 2 units to the right, x minus 2 all squared. 2 units to the left, x plus 2 all squared, right? Then they do the same thing with the cubic, right? The x cubed, this is what the cubic looks like. They do the same thing with a linear function. They give you 2x, and they're going to 4 up would be 2x plus 4, right? Now, by the way, this, just so you remember, this is a circle again. I would ignore this, but this is not a function, right? We already know that. So we're not really going to be studying it in this unit. You won't be doing transformations on circles because it's not a function, okay? And now, again, some more notes for you. It just says, in the examples below, we start with the original relation point. So they gave you a point, and they kind of did it backwards, right? So we can look at a couple of these together before I give you some work time. So if I cover this up, my original point was 2, 7. It got translated to 5, 9. Could you, in your head, or doing some kind of math, could you figure out what translation had to happen to move from point 2, 7 to 5, 9? What happened to the x value? Got bigger by 3, right? So it should be 3 to the right and 2 up. And sure enough, that's the mapping. So we say 3 to the right, 2 up. So that's all they're doing here. Here, if this was my original graph and then it ended up looking like this, right? I would probably write it like this. And I'd say, okay, the difference between this equation and this equation is just 6 up. That's it, okay? So again, this is just nice to maybe to refer back to. They include some absolute values, some squares. The only thing they didn't include in this little chart is something like this. If I gave you, if your original graph was f of x, I'll add this one here, and I gave you this, y equals f of x minus 7 plus 4. Okay, what change is indicated here? From if this was my original and this is my transformed graph. Yeah, I'd say 7 units to the right and 4 up. We did quite a few of these though in our examples, right? That's it. Okay, so I'm going to assign you exercise 1.3. Kind of has a mixture. It starts off with an f of x, then it jumps to an actual quadratic equation. So I'll give you some time to work on those. Not the whole class, like not an hour, but maybe about half an hour. So it goes on to the next page, 1 to 9. And then we are going to talk about compressions and stretches. We'll start talking about them today. Those are a little tougher, right? It shouldn't be a surprise because they involve multiplication, right? Multiplication and division, I guess. And anything with multiply and divide is generally a little harder than adding and subtracting, right? Not a whole lot, but. Okay, I'm going to take, if you need a break, we'll take a break. You've got like 25 minutes or so to work on this, so you've got time to run for coffee if you want, whatever. Let me just take attendance first, though. EB is here. Yeah. Abdullah is here. Spencer's here. Nadine?
Yes, you do.
Nadine?
Yes.
Nadine. Okay. Dennis is here. Adam's here. Eduardo's here. Cody? No. Robiel? Ibrahim? Dee is here. Joby's here. Minyang? Jack is here. Carl? Justine? Ryan? Where's Ryan? There he is. Noradin? Neville is here. Joanna's here. Amanette is here. Chris is here. Walker? Where's Walker? Waleed? Waleed? Not here today? Okay. Lena? Johannes is here. Dong is here. No, he's not here. Burhane? Burhane, okay. Joshua? Thomas? Alejandro? Rahel?
Yes.
Rahel? Ercolano? And Eileen is here. whose name I did not call? I don't think so. Hey, Abdel, I'm gonna get you to go to a different classroom today, because Elsie's super busy, and so I'm gonna get you to go down to mine.
translates it to, I think we're gonna be some, did this one last week. Beginning with the graph, beginning with this graph, okay? Sketch the graph that translates it to this. Doesn't make sense.
That's what I'm
Wait,
thinking, like,
why
what
did
is
it
it?
make sense last night? I actually worked through all these so that I would be, yeah, let me just read this again. Beginning with this, yes, sketch the graph that translates into.
So what I trying to do, like what I just applied it to show the graph, the graph, this is the like, this is the form.
This is the basic English language, right? And sketch the graph translates into this. I could describe the changes. The changes that would be required to move from here to here. Read the right two up. That's what it would
Oh,
be, right?
okay.
So I don't know if you wanted to, that's what because it would be read the right two up, right? Read the right two up.
See, it's a one.
So they just, I don't know why they would just say that. Sketch the graph of this, right? So it's only one. Yeah, they're just saying sketch that graph. That's
Okay,
weird.
see
Yeah.
that?
Okay, Eduardo and I took I took longer. Number 3 is really, it's written in a really weird way. It says, beginning with this, sketch the graph that translates it to this. Basically, scratch out this. Just sketch the graph of this. That's all they're looking for. I'm not really sure what that was all about. It's kind of confusing. And remember, anytime you see the word describe, you have to use a couple of words, right? It's not enough just to show me math, it has to be words. Did you? Oh, I was going to wonder where it went. I was going to look ahead at my new examples.
onto here, right? So basically you're saying take 3 away from x, add 2 to y. Yeah, minus 1 plus 2, yep, that's it. And the answers, I gave you the answers, right? Okay. Here are the answers? Yeah. So those are the answers to each of the answers that we have. So we're working with this. You're working with this. Okay.
Yeah, that's not a bad thing to do. A little pricing.
If you get finished early, you could start reading about compressions and like on the next couple pages of notes, but I'm gonna be going over some, before class ends, I just wanna introduce stretches and compressions today. So I'll give everyone a few more minutes to keep working. Just gonna
Be right back. I'm just gonna write it down. Oh, sorry.
2 every day. So if you're around school, like at 10 o'clock, I'm just in the library. There is math resource help offered throughout the day on every slot, and there are other math teachers and resource from the library that can help you with this. Okay, and I'm in slot 2. If you want to see me, everyone's got how to handle on this assignment. Right? And again, it's kind of nice to have those notes coming up, right?
I don't see a lot of issues with people on the assignment, so maybe I will start.
And if you didn't quite finish, you can finish that homework. Well, this is what you were looking at. We were working on this one. Because it said plus 4, that's a shift left. That left. And so when I look at the x-axis, right, this is the x-axis. When I move left, I'm subtracting. When I move right, I'm adding. Okay?
One of the things I was just talking about with one of the students is you can also use your like the x-axis is a horizontal number line, right? So just think about it. When you're moving right on the number line, you're moving to the positive side, right? So you should be if you're doing mapping, like you're adding numbers to the value. The value's getting bigger. When you're moving left on the number line, you're subtracting, right? Even though the equation shows up x plus 4, you know, most of you seem to get the plus 4 as a move to the left. You can just determine if you're moving left or right, your number line will tell you whether to add or subtract, right? All right, I think I'm going to introduce the stretches and compressions. I don't know how far we'll get, but I'm going to introduce them. And I might not have a lot of more homework for you. I think I'll have an assignment for you to do tomorrow just so you can practice your skills and I can give you some feedback. If you didn't quite finish assignment 1.3, I'm going to get you to do that finish it up at home. And I'm on to back to the purple book. So we're going to talk about, I call them stretches and compressions. I think your book refers to them as expansions. So expansion is another word for stretch. It means generally getting bigger, right? Either getting taller or wider. That's what a stretch is. Generally, we use the word taller for getting stretched vertically, right? Or wider if I'm talking about a horizontal stretch. And compress means that something gets smaller, squeezed either down or squeezed in. Now, here's where we get a little weird, but it's not so weird if you consider that x always seems to cause problems, right? Doesn't the x value always cause a bit of problem? All the questions that we've had so far kind of involved x. Would you agree? Yeah. Like when you see this, you're trained to say, oh, let's move to the left. Even though there's a plus sign there, right? Because normally it's supposed to be minus. Y is really straightforward, right? When you see plus 3, it's up. Minus 3, it's down. X is always the guy that causes problems. And he continues to cause problems when we do stretches and compressions, as you'll see in a moment. So let's go back. We're just going to start studying generic a general, we're approaching this from a general viewpoint. So just from an f of x, I'm not talking about any particular function. For a function y equals f of x, a vertical compression or stretch is defined by a multiplier outside of the f of x, right? Because generally speaking, remember that f of x can be regarded as another name for y. Some people will say that. So it's basically telling you multiply the whole function value, multiply the y value by a, okay? So it's as straightforward as that. It's really easy. So notice this, if a is between, we say the absolute value of a because at this point I don't really care. Just look at a, whether it's a -4 or a +4, the graph is still going to get bigger. If it's a fraction though, if a is between 0 and 1, there's a vertical compression, okay? So if you're a little rusty on your symbols in math, this basically means if a is between 0 and 1, okay? Now, I could say if a is a fraction, but I hesitate to say that. Like, most people think of the numbers between 0 and 1 as fractions, but I don't want to say if a is a fraction, the graph gets smaller, because that's usually the case. But what if a could be the fraction, I don't know, 12 over 5, right? Agreed? 12 over 5 is 2.5, right? So that's not a small number, that's a big number. So I can't just say if a is a fraction, but normally you'll see are the fractions that a will be given to you as like a half or a third. You know if it's a fraction between 0 and 1, that means the original graph is going to get compressed, it's going to get smaller. And there is a vertical compression by a factor of a, and so what we do is we multiply each y value by a. Whatever a is. If a is a half, y gets multiplied by a half. If a is greater than 1, there's a vertical stretch by a factor of a, right? So whatever a is, doesn't matter if it's a fraction or a whole number, we just multiply the y value by a. Now, we're kind of going to do reflections at the same time, because all that a reflection is, if a is less than 0, there is a reflection in the y-axis as well as the stretch or compression. So basically, I'm just going to say to you, if a is negative, the graph reflects over the x-axis. Remember I talked about that yesterday? Because if a is negative, it's saying multiply all the y's become their opposite, right? Their opposite value. So this is my y-axis. If y was 4, it's now going to become a negative 4, for example, right? It's going to flip over the x-axis. So the y, any stretches involving the y coordinate and a values, a's are really easy to deal with. All right, let's take a look at the other type of stretch we're going to look at. Guess what? It's the stretch or compression on the x value. So let's look here. For a function y equals f of x, a horizontal stretch or compression is defined by the b value, okay? So a controls the vertical, b, and can you see the difference in position? B is inside the brackets acting on the x, okay? B acts on the x value. And I'll just do this too. A acts on the y value. Okay. So sit tight, because if b is a fraction, so same thing, there's a horizontal stretch. The graph gets wider, just like parabolas. Remember when you had that half a squared, the graph got wider? So if b is between 0 and 1, the graph gets wider. Okay? If b is greater than 1, the graph gets narrower, right? Smaller. Now, how does that happen? That doesn't make sense, right? Because if b is a big number, let's say b is 10. How do I, if I'm going to be multiplying the y values by 10, how does the graph get narrower? Well, guess what? It doesn't, because b doesn't operate like a. A is really straightforward. We always multiply by whatever a is. B is always multiplied by the reciprocal of b. So if b is a small number, like 1/2, we multiply the x values by 2. If b is a large number, like 5, we multiply the x values by 1/5. So b, we don't use b to ever be the multiplier. It's 1/b, meaning the reciprocal. Okay? And again, if b is negative, there's a reflection in the y-axis. If b is negative, the graph reflects over the y-axis. Okay. So it gets a little confusing at the beginning, but you'll slowly adjust to it. I guess I'll just say too, I'm going to kind of run out of room, so I'm going to, maybe I'll do up here, okay? All my little notes here, I'm just going to write up here. In summary, multiply each y value by a and each x value by the reciprocal of b, which is what 1/b is, right? 1/b. 1/b means the reciprocal of b. I think it's the language is easier to understand the reciprocal of b, because let's say b is 2/3, then you're going to multiply by 3/2. Okay, so let's put this into practice. This is where I think kind of selecting a couple critical points and doing that mapping technique really kind of clears away a bit of clouds and confusion for students. I know some teachers do their transformations all on the graph and they just took a couple of points and transform, but I'm actually always going to do the mapping, okay? That means I have to pick a couple of critical points. So my critical points, for sure this is a critical point, right? I think this is a critical point too, because I can see it like right on the grid lines. And I'm going to pick one more point. I can see this one over here, the point 1, 2, because they clearly cross on clearly defined grid lines, right? So I'm going to do my critical points, whatever I chose for my critical points, my xy points. So what was that? -3, 0. What were the coordinates here? -2, 1. And the last one, 1, 2. And I think that's fine. 3 points is enough for this. Okay, I consult this is just f of x, right? That was just given to me, my generic f of x. And they want me to graph 2 times f of x. So what transformations are they wanting me to do? Can you describe in words? What kind of transformation is this? It's acting on the y, right? It's an a value. So we say it's a vertical stretch by a factor of 2. Agreed? This is an A value. A's are clean cut. So that means there's no change to my X value. Agreed? Do you see any changes to X? I don't. So X stays the same. And I'm going to just multiply every Y value by 2. So if I'm showing, nothing shows your arithmetic, right? That's it. So this gives me a way to show my work, to go back to my work if something doesn't look right on my graph. So my X stays the same. So maybe I'll just record all my X's. They stay the same. I just double my Y's up. Well, nothing happens here. 1 times 2 becomes 2. 2 times 2 becomes 4. These are my new points that I have to plot. Notice I recorded them in order, moving left to right. I'm going to plot them in order. So I have a -3, 0, so my origin stays the same. -2, 2, and a 1, 4. Okay? Connect in the same smooth. If you see a smooth curve, your shape has to look the same. Now we expected, we knew it was a vertical stretch by factor of 2, so the whole graph should have been stretched up. Does that look like a stretch up? I think so. It's steeper, right? The climb happened like this was a shallow climb, it climbed steeper, faster. So this would be my graph of y equals 2f of x. Again, I wasn't given the actual equation, so I'm just stuck with using the general form f of x and 2f of x. Okay?
I don't understand how you bring the reflection plan, the points 0 to 4.
I just picked nice points that occurred. I just picked 3 points. I just picked any points that I thought would be easy to plot. Okay, so vertical stretches are easy, right? It's the horizontals that can get a bit tough. Let's try this vertical though. Let's try one more vertical and then we'll, I do want to get to a horizontal too. Okay, given the graph of f of x, sketch the graph of a third. Now again, you probably could maybe do this without picking critical points, but like I said, I'm always going to pick my critical points. So here, Annette, these ones have been decided for us, right? But even if the points hadn't been plotted, I would have picked the corner points anyway. So I've got what, -1, 1, 2, 3, 4, 1, and 6, 6. Okay, what changes do you see here? 1/3. A equals a third, right? So what do we call that? That would be vertical compression. So this is the language I'm going to use, okay? Vertical compression by, notice how over here, sorry, I said by a factor of 2. A equals 2, vertical stretch by factor of 2. So I say vertical compression by a factor of 1/3. So for me, when I say by a factor of, that's your multiplier. That's what you're going to use to multiply. Okay? So vertical, nothing happens with the x. And what do I have to do? Every y value is multiplied by a third. And again, fractions become important. Multiplying by a third is the same as dividing by what? 3, right? So you could, if you wanted to do it that way, you could, right? You could just say, okay, well, dividing by 3. However you want to do it. My x's remain unchanged. Okay? All right. 1/3 times 1 is? 1/3. 1/3 times 3 is 1. 1/3 times 1, we already established, is a 1/3. What's 1/3 times 6? Thank you. Okay, so this one I'm going to have to kind of guesstimate a bit. My graph isn't great, but I'm going to graph. First of all, sorry, what do you expect to happen to this graph? It's going to shrink, right? Is the domain going to change? Will the width of it change?
No.
It shouldn't, right? The width should stay the same. The range will change, right? It's going to it should shrink down, so that it should be shorter, but the width should stay the same, right? Okay, so -1 1/3. I'm going to kind of guesstimate where 1/3 is. 2, 1, 4, 1/3, and 6, 2. Now this graph is harsh, meaning it's got straight angles, sharp corners. So this is something I would use a ruler for. So harsh lines, everything's connected very strongly. Okay, so we thought that the graph would be shrink. It sure enough shrunk, right? The domain, the width is the same, so that looks good. That's what a vertical compression looks like. Everything was squashed. Yeah? Okay, finishing off with vertical stuff, determining coordinates of image points after vertical stretch or compression. Here's your point A. This is your graph. What are the coordinates of image of A primed on -5x²? Okay? So see if you can come up with an answer. What are the coordinates of A primed? Okay, what's happening here? This is a vertical stretch. And because of the negative sign, it's actually going to be reflected over the, right? And reflection over x-axis. Okay. Now, we don't have to graph this, so it doesn't really matter. All we're doing is coming up with the coordinates of A primed. Okay, so what are the coordinates of A primed? Are there any changes to the x value? I don't see any, do you? All we have is A equals -5, right? Okay, so the x value stays the same. So what happens to the 14? The 14 gets transformed. It should get larger, right? Is it 70? Sorry, I had something different. Okay. That's a much larger number, right? Even though it's negative, it's a huge negative number. So the graph, whatever it is, will be flipped over and stretched quite a bit. What about this? The point B lies on the graph of the root of x. What are the coordinates of 4 root x? Again, A is 4. So this is a vertical stretch by a factor of 4. This one I think we can do in our heads easily. B primed will have the coordinates. Nothing changed on the x value. But it's going to be, what, 36? Again, a huge stretch. Notice the A positioning. It's right outside brackets. It's outside a root sign. It's outside of anything that is enclosing or encasing the x. Okay? All right, let's get to, because this class is technically not over till I think 5 after. I'll have to get adjusted to that. Let's take our first look at a horizontal. These are the toughest. Of all the transformations, these are the toughest kind, horizontal stretch. Can your eyes see the difference between an A value and a B value? But you tell that this is a b value?
B value.
Yeah, because it's inside, right? It's multiplied right beside the x. It's right by the x. It's multiplying right on the x. So my first job is to make sure you can see the difference between, because if this was an a value, it would be this, right? It would be y equals 2 f of x, right? That's the a value. This is the b. Okay, b equals 2. So b is a large number, bigger than 1. If b is bigger than 1, is this going to be a horizontal stretch or compression? Compression. It does the opposite of what you think. So, the graph is compressed horizontally. Okay, so what this means mathematically, the reason it's compressed, okay, we multiply each x value by the reciprocal of b. Well, what's the reciprocal of 2? 1/2, yeah. Okay, so let's pick some critical points again. Again, they weren't identified, but I'm going to pick my corners. It's kind of a weird little shape, right? It's almost a V with a little broken leg here. So these are my critical points. And it's hard, like I say, the graphing gives you, it's kind of clear cut when you pick your critical points and you math. There's not a lot of questions. So what do I have here? I have -4 and 0, -1 and 4, 2, 2, and 3, 0. All right, so this is the math that I have to do. There's no changes on the y this time, but every x is multiplied by 1/2. And again, for fractions that are like 1/2 or 1/3, sometimes it's easier. Multiplying by 1/2 is the same as like cutting something in half, dividing by 2. Okay, so if I divide all my x's by 2, what do I get? I get -2, right? -4 divided by 2. -1 divided by 2, I'll just record that as -1/2. 2 divided by 2, cut in half. Half of 2 is 1. Half of 3 is 1.5, right? Okay, those are all my x values. My y values, there's no change. So I just re-record them. Okay, now I'm ready to plot my new graph. So I have, and I expected, a good math student kind of should know the ballpark of the answer or know what to expect. So I'm expecting this graph to be compressed horizontally. My final picture should be narrower, right? Okay, let's see. -2, 0. -1/2, 4. 1, 2, it looks good so far, and 1.5, 0. Again, I'm going to use a ruler because it's very linear, this graph. So I've got my first section, my second section, and my final. Does that graph look like it's compressed horizontally? Is it narrower? Yeah. Okay, I'm just gonna, yeah. This time it asked me for domain and range too of the transformed graph. So my blue graph, the one I did in blue, that's the graph of y equals f 2x. And I'll do the domain and the range. Okay, what's the domain of my transformed graph? -2 to 1.5. Okay, so I'm going to say -2, 1.5. And I use square brackets for the endpoints, right? Why do I use the square brackets when I use interval notation? Yeah, those points are actually included, right? There's actually point values there. And my range is from 0 to 4. Both 0 and 4 are included, so I use square brackets. I think I'll do this last example and then I'll leave you with finishing assignment 1.3 if you haven't finished it. And read those notes at the beginning of section 1.4. Kind of basically it's just giving you a lot more info on stretches and reflections. So let's do this last picture. Given the graph of y equals j of x, sketch the graph of y equals negative half x. So b equals negative a half. So if b is small, the graph gets big. So that means it's a horizontal stretch. We multiply each x value by -2. I'll say horizontal stretch and a reflection, right? Reflect over y-axis. Okay, multiply each x value by 2. Again, this is my radical. You'll notice that I always pick, there's usually 3 nice points you can pick for a radical function, right? The original, the starting position, and usually the next point, because this kind of corresponds to your point 1, right? And usually there's one more nice one, and sure enough, here it is. By nice, I mean it's landing right on the grid, so I can use those coordinate points easily, right? So once again, I'm going to record my critical points. -3, 0, -2, 1, and 1, 2. Okay. So I'm going to multiply every x. My math is -2 times x, no change to the y. So -2 times -2 times -3 is 6. No change to the y. I'll get a +4, no change to the y. And I'll get a -2, no change to the y. Okay, so I'm going to draw my new graph. Before I pick my pen up and draw my new graph, what do I expect is going to happen? It's a horizontal stretch, reflect over y. When this graph gets reflected, what's going to happen to its, can you describe what's going to happen physically to it? The whole thing flips. It should end up pointing this way, right? My starting position should be here. So remember that. Okay. So 6, 0, 4, 1. Okay, looks good. And -2, 2. Okay, remember I told you order is important? This was the order I recorded my points in. This is the order I plotted them in. That tells you the order to draw them in, right? 'Cause here it's starting to get confusing already, right? So I start, this is my original point. This is where the graph starts, the origin. So plot it this way. I guess all I'm saying is if you weren't really paying attention, you could easily draw it that way, right? And the new graph, so this is my graph, y equals j -half x. Okay, so it did what I thought it was going to do. It's kind of hard to see the horizontal stretch. To be honest, it's a little hard to see on radicals, but it's definitely reflected. And if you look at it, I can see the horizontal stretch because this is my original graph. What's the horizontal distance between the first 2 points plotted? It's just 1 unit, right? Agreed? The horizontal distance from this point to this critical point is just over 1 unit. Look at our transformed graph. What's the horizontal distance from point 1 and point 2? 2 units, right? So it has been stretched. It's a little hard to see. Okay, I'm going to leave it there. We'll finish up examples tomorrow. Please finish assignment 1.3. And you can read up a little bit on the notes too for the next section in your textbook chapter, okay?